pop up so you can.
Are we on the air?
Yep.
Good morning, students. This is new for me. We're going to try and do this remotely. We'll see how it works. Mr. Schaff is here helping me. I'm very thankful to him for doing that. And we're going to try and make things as normal as we can during this time that we're out of school so that we can continue on with our curriculum as we need to. So today, this is what we would have done today in class. You had homework today that was on freezing point, which we went over Friday, which that was to be turned in today. Obviously, it's not. We'll worry about that later. Today, we're going to finish up the notes packet on Unit 10.2, which is on colligative properties of solutions. Talk about the difference between using an electrolyte solute versus a non-electrolyte, which involves something called the Van Hoff factor. So we'll be doing that. You have a homework assignment for that that will be due tomorrow. Tomorrow is going to be Lab 10.2, ice cream. Obviously, we won't be doing that tomorrow, but we will be doing it. So assuming we return to school, that will be one of the things that is up on our agenda first. And again, as I told you Friday, the Unit 10 exam, which covers both Unit 10.1 and 10.2, would have originally been scheduled this Friday. Again, that is on hold until we figure out what we're doing. So, but you do already have the review for that, which you'll be doing. So anyway, I think we're ready to move on to the notes. So there they are. So we're on this page of our notes, and we'll go ahead and get started. So the first thing I want to talk about today is you can also determine the molar mass of an unknown solute or any other unknown regarding the solution by knowing how the addition of that solid affected the freezing or boiling point of the solution. So normally we have used all of these equations here in a multi-step process to determine any one of these variables as an unknown, but we actually have a way of combining them into one kind of handy-dandy little equation. So if we start with this one here, where the molality of a solution is equal to the number of moles of solid over the kilograms of solvent, and either the change in freezing point or boiling point, either one, is equivalent or is equal to the freezing or boiling point constant times the molality of the solution. I'm going to substitute in this first equation for M here, and so we have the change in the freezing point is equal to Kf times the moles of solute over the kilograms of solvent. I'm going to multiply both sides by kilograms of solvent and cancel that out. And so far, this then is what we have. The kilograms of the solvent times the change in the freezing point, again, that could be boiling point, equals Kf or Kb, as the case may be, times the moles of solid. And then the last thing I'm going to do is then substitute in for moles the relationship we have between moles mass and molar mass, which is N equals M over M. So I'm going to go ahead and do that now. So now we have the kilograms of the solvent times the change in the freezing point equals Kf times the mass over the molar mass of the solute. Just did a substitution there in for N. I'm going to multiply both sides by molar mass of the solute, which then those will cancel. And so now we're left with our final equation here, where the molar mass, and I'll label this so we know what's what, of our solute times the kilograms of our solvent times the change in the freezing point, could be the change in the boiling point again, is equal to Kf of your solvent, again, could be Kb, times the mass of the solute. And this then is kind of a catch-all equation that would allow us to solve not only the molar mass of our solid, but actually for any of those variables. So we'll go on now to the next page and I'll do example 10 for you. There we go. Okay. Okay, so example 10. Freezing point of a solution is minus 0.390 degrees Celsius when made by adding 3.90 grams of an unknown solid, so there's our mass, to 475 mLs of water. So with water being our solvent, again, and a density of 1 gram per ml, 475 mLs is equivalent to 475 grams. So we can then just divide by 1,000, remove the decimal 3 places, to the left, 0.475 kilograms. We are looking then for the molar mass of the solute. Before we do that, let's look back up here at the freezing point of the solution. So that is the new freezing point temp. And so to find the change in the freezing point, that would be, remember, water's original freezing point as a pure solvent is 0. So it'd be 0 minus negative 0.390 or 0.390 degrees Celsius. That would be the change in our freezing point temp. All right, so we're going to utilize this new equation that we just derived. So this is the molar mass of the solute times the kilograms of the solvent times the change in the freezing point temp is equal to Kf times the mass of the solute. So mm we're looking for, our kilograms is 0.475. Change in the freezing point, 0.390. Kf, remember Kf is a constant. We pull that off the chart that you got in class the other day. For water, that is 1.86. And the mass of the solute was given at 3.90 grams. So we're solving for molar mass, so we're going to divide both sides by the product of these two numbers here next to molar mass, which is 0.18525. And when we do that, and looking back at the original data, 3 sig figs in our answer, 39.2 grams per mole. So given any freezing or boiling point data, we can determine not only molar mass, but any other variable, any other quantity involved in one of these types of situations by utilizing this kind of catch-all equation that incorporates all of those things. Okay, the last thing I want to go over in this particular unit is regarding electrolyte solutes as compared to non-electrolytes. So early investigators were puzzled as to why the addition of an electrolyte solute to a solvent lowered the freezing point or raised the boiling point more than adding a non-electrolyte solute did. For example, a 1 mol solution of sodium chloride lowered the freezing point of water twice as much as a 1 mol solution of any non-electrolyte. And a 1 mol solution of calcium chloride lowered the freezing point of water 3 times as much. That they were puzzled by that initially until they figured out what exactly happens when you dissolve an electrolyte solute in water as compared to a non-electrolyte. The reason is because when you dissolve an electrolyte solution, it breaks apart. Remember, water drives itself between the molecule and because of its polarity. Remember, it's negative end is attracted to the positive ion in the solute. Its positive end is attracted to the negative end of the solute, and it splits it apart. We've talked about that many times, ionization or dissociation. However, when a particle of a non-electrolyte dissolves in water, such as sugar, sugar dissolves in water because it has a polar end, and thus water is attracted to that. But it does not split the molecule. Water simply surrounds it and dissolves it without splitting it into ions. And so there's only one particle in solution. So as we look at these three solutes here that all dissolve in water, the first one, as I mentioned, is sugar. This is a non-electrolyte that does dissolve in water. So we start out here with a solid, and we put it in water, and it does dissolve into an aqueous solution, but the molecule remains intact. So it doesn't split. Only one particle in solution. However, when you dissolve sodium chloride in water, sodium chloride is an electrolyte. It's an ionic compound. Dissolve it in water, as we well know or should know by now, sodium chloride splits into two ions that form sodium chloride, which is one sodium ion and one chloride ion. So it splits into two particles in solution. Calcium chloride, another ionic compound, soluble in water, also an electrolyte. When you dissolve calcium chloride in water, recall then that it splits into three ions, a calcium ion and two chloride ions, for a total of three. So it splits into three particles in solution. And therein lies the explanation as to why an electrolyte would lower the freezing point or raise the boiling point to a larger degree than a non-electrolyte would. The increase in effect on colligative properties by electrolyte solutes as compared to non-electrolyte solutes is called the Van Hoff factor. The Van Hoff factor, named for the person who discovered it, and it is labeled I. It's kind of an italicized lowercase I. So if we look back up here, any non-electrolyte solute has a Van Hoff factor or an I factor of 1. But once you have an electrolyte, it's going to depend on how many ions the electrolyte is split into when it's dissolved in water. For sodium chloride, since it splits into two ions, the Van Hoff factor or I factor is equal to 2. For calcium chloride, I equals 3. The larger the value of I, the bigger the effect it's going to have on the freezing or boiling point of the solution. So let's advance this. Go. And so to summarize that, for all non-electrolyte solids, I equals 1. So it can be ignored. It can be ignored. So we look at our boiling point equation here. A change in boiling point was equal to Kb times N, but it's actually, if you have an electrolyte, it's Kb times N times I. But if I is equal to 1, like I said, if it's a non-electrolyte, it can be ignored. Same for freezing point. Not only for this equation would that be true, but for the equation that we just derived, kind of the catch-all equation for all colligative property solutions, So mm of your solute times kilograms of your solvent times the change in the boiling point or the freezing point, I have boiling point here, is equal to Kb times the mass of the solute now times I. And again, if it's a non-electrolyte, I would be equal to 1, which means you could ignore it. But if it is an ionic solute that's going to split into ions, then I is going to have a value of greater than 1, minimum of 2. And so it would have to be included and taken into account when you do the calculations. Okay? So this was our shortcut equation for any variable involving for freezing or boiling point of a solution. All right, so next example, we're going to utilize that along with the Van Hoff factor I to determine basically the same types of calculations we've done previously. All right. So the next one, number 11, what is the boiling point of a solution? So we're looking for the new boiling point temp that has been made by dissolving 105 grams of NaNO3, so that's the mass of our solid, in 675 mLs of water. So our water is our solvent. That needs to be in kilograms. Again, an ml and a gram are the same for water. So if we just move the decimal 3 to the left, that would be 0.675 kilograms. All right. So we could do this either the short way or the long way. So I'm going to show you the short way first. We'll do it the long way second. And then as far as I'm concerned, you can do it the short way if you want. That's probably what I would do. So anyway, let's look at that. So the shortcut method would be to utilize our catch-all equation, so to speak. So the molar mass of our solute times the kilograms of our solvent times the change in the boiling point here would be equal to Kb times the mass of the solute times I, the Van Hoff factor. Sodium nitrate is an ionic compound. It is going to split into ions when it is dissolved in water. And being sodium nitrate, it contains two ions. So when that solid is put into water, it's going to split into a sodium ion and a nitrate ion. Both, of course, of those are aqueous, and so I is equal to 2 for this particular solute. All right. The other thing we would need to know is the molar mass of our solute, NaNO3, which would be 23, 14, and 48, which would be 85 grams per mole. So, molar mass 85 times the kilograms 0.675 times the change in the boiling point, which we do not know, is equal to Kb for water 0.512 times the mass of the solute, which is 105 grams, times the I factor, which is 2. We want to divide by the product of the two numbers in front of the boiling point change, so we can isolate that. That number is 57.375, so we want to divide both sides by that. And in doing that, the change in the boiling point then is equal to 1.87 degrees Celsius, that is to 3 sig figs, which means then the new boiling point, remember for boiling point, we add the change to the original boiling temperature, which for water is 100 degrees. So the new boiling point temp would be 100 plus 1.87, or 101.87 degrees Celsius. Again, keeping the decimal places there so we get a more precise answer. So that would be the shortcut method of doing this problem. I'm going to show you the regular method as well. It's a bit longer, but I want to show you that we do get the same answer, and that is doing the calculations in a series of steps. So let me erase this here a little bit, and we'll do that. So what I would do first then, if I'm going to use the regular method, is to first solve for the number of moles of our solute. So N is equal to mass over molar mass, which is 105 over 85. Again, this is an intermediate calculation, so we won't round this at all. 1.23, 529, 4118 moles. Again, no rounding there. The next thing would be to find the molality of the solution that we just made. So we would take the number, which is N over kilograms, moles over kilograms. So 1.235, 294, 118 moles over the kilograms of our solvent, which was 0.675. And that to 3 sig figs is 1.83 molal. Next, change in the boiling point. Delta TBP equals KB times molality. KB again is 0.512. Actually, I'm sorry, KB times M now times I. With this being an ionic solute, we got to have the I factor now incorporated there. So that would be 0.512. Times the molality, 1.83 times I, which is 2 ions, 2 particles. And again, that comes out at 3 sig figs to 1.87 degrees Celsius, just like it did before. And so then our new boiling point temperature, 100 plus 1.87, 101.87 degrees Celsius. Same answer as we had before. This way, of course, was done in a series of steps. That's what's nice about that catch-all equation. We can kind of do it all at one time. So you can do it either way. If you want to save yourself some time, we'll do it the short way. All right, last one. Erase this here and advance the screen. There we go. So for the last one, what is the freezing point of a solution? So we're looking for the new freezing point temp that has been made by dissolving 125 grams, which is the mass of our solute of aluminum chloride. So aluminum chloride is our solute in 925 mLs of water, which would then be, of course, 0.925 kilograms. All right, so with aluminum chloride being our solute, we're going to need its molar mass. Aluminum's 27. 3 chlorides. Remember, chloride 35.45 times 3, 106, which is 133 grams per mole. And the other thing is aluminum chloride is an ionic solute, meaning it's going to split into ions when it's dissolved in water. And so when that occurs, it splits into actually 4 ions, an aluminum ion, which has a +3 charge, and 3 chloride ions, which each have a -1 charge. So 4 ions total, so the I factor is equal to 4. So we'll do this the short way. So the molar mass of our solute times the kilograms of our solvent times the change in the freezing point temp is equal to Kf times the mass of the solute times the I factor. So our molar mass is 133 kilograms of solvent, 0.925. We do not know the change in the freezing point. That's what we're going to determine. Kf for water, 1.86. Mass of the solute is 125 grams. And we said our I factor is equal to 4. So we're going to divide by the product there that's next to the change in freezing point, which would be 133 times 0.925. So we're going to divide both sides by 123.025. On the left side, of course, that will cancel. So the change in our freezing point temp to 3 sig figs would be, one moment please, 7.56 degrees Celsius. That is the change in our freezing point. So the new freezing point temp then, and remember with freezing point, we subtract the change in the freezing point temp from the original. For water, that would be 0 minus 7.56 or negative 7.56 degrees Celsius. And the Van Hoff factor, the I factor, is exactly why we don't use a non-electrolyte solute when we're salting the roads in the winter, right? We could dump sugar on the road. Believe me, it would work. It would melt the ice, but not to the degree that calcium chloride will, which is what we use, because sugar is a non-electrolyte. Its Van Hoff factor, its I factor is 1. Calcium chloride has an I factor of 3. It's going to drop the freezing point 3 times as much as sugar is. That's why we use it. Some have asked, well, why don't we use aluminum chloride? It has an I factor of 4, and you can actually we have compounds that have I factors of 5. Why don't we use those? Well, it has to do with availability and price, right? Calcium chloride is cheap, it's plentiful, it's easily obtained, and so taking that and it works well. So taking that into consideration, it's probably the best choice we have right now. So that's why we use it. So anyway, that concludes the lesson for today. We have an assignment over this, more colligative properties applications. You should be able to complete that now. The answer key to that, as well as all answer keys while we're doing remote learning or e-learning, will be posted to my Canvas website. I've created a page especially for that. It is labeled answer keys for e-learning. You will find it there. So that concludes today's lesson. Do that assignment. It would be due tomorrow. You also then should have your review. And so there again, you should be able to complete that now. See you next time. Take care until then.